Good evening, everyone. I'm Krishnaveni. I'm a final year computer science student at IIT Goa and a student member of ACM Goa professional chapter. On behalf of the chapter, it is my pleasure to introduce our distinguished speaker for today's tutorial session, Dr. Divya Padmanabhan. She's an assistant professor at the School of Mathematics and Computer Science at IIT Goa. Previously, she was a research fellow at the ESD pillar of Singapore University of Technology and Design. She received her PhD from the Department of Computer Science and Automation at Indian Institute of Science, Bangalore, and holds MTech and BTech degrees from IIT Madras and NIT Calicut, respectively. She's also worked in the software industry with Oracle India for a couple of years. Her research interests broadly span robust optimization, decision making under uncertainty, reinforcement learning, and machine learning. Outside of academics, she's a trained Carnatic classical musician. Today, Divya ma'am is going to be conducting a very hands on tutorial to develop fundamentals in the area of reinforcement learning. So, without further ado, I invite you to join me in giving a warm and enthusiastic welcome to Dr. Divya Padmanabhan. Over to you, ma'am.
Thanks, Krishnaveni, and also ACM Goa for inviting me to give this hands-on tutorial. So at the outset, I would like to make it as hands-on as possible. But yeah, I do understand that there are a lot of initial hurdles when people try to get in to reinforcement learning, especially in terms of the math and stuff. So what I thought would be a good thing to do today is to get people introduced into reinforcement learning, some of the basic things which otherwise is quite like cumbersome when you get into a textbook, like directly when you get into a hands-on session, hands-on. Okay, so that's the plan. So I will what I'll do is I'll just introduce you to some things in MDPs, which is like a crux for reinforcement learning, and then we'll go into the actual concepts of RL. Okay, so I'm assuming a lot of attendees here are students. So please feel free to stop me at any point. Okay, I have just 22 slides. Okay, I don't know if 1.5 hours is really enough for 22 slides, but just make it as interactive as possible, because that, and especially in the online mode, that's when you benefit the most. Okay, so don't think that it's a silly question or anything. There's no silly questions. Please feel free to stop me if something is unclear. Okay. Um, all right. So, so I just want to start off with some use cases. It's a hands-on session, so I won't delve too much into these use cases. It's just to motivate the area of reinforcement learning. So there are a lot of applications that you might be seeing, things in robotics, game development, things like chess games, Pac-Man, all of these things. Designing automated agents for all these games. Okay, and there's a lot of tasks in the industry which get automated, and there also reinforcement learning plays a huge role. So recently there was news of Google servers being managed by an RL agent in terms of the battery management and things like that. Okay, so like that, there are a lot of such use cases. And of course, from time immemorial, there have been use cases of MDPs and RL in finance and trading too. And this figure here that you see is a self-driving car, which is like, now there's a lot of development in this area. And RL is one of the key players here in self-driving cars. So I think there's enough and more motivation to look at RL today. So in today's talk, as I said, I will first talk of Markov decision processes, um, which is actually the foundations for reinforcement learning. And we look at, MDPs and the optimal policy computation in MDPs. And then we'll move on to the RL setup, which deals with the case where some things in the MDP is not known, some parameters in the MDP are not known. And reinforcement learning is essentially a way of learning or dealing with the situation where some parts of the MDPs are known. Okay, so that is the last 2 points are actually the reinforcement learning setup. And we'll get into the policy learning in that space when you don't know some aspects of the MDP. Okay, and a general prerequisite for this area is probability statistics. A lot of things in probability statistics get applied here. Things like conditional probability, expectations, Markov chains, and law of large numbers. So this is something you should be comfortable with. So is there a question? Fine. Okay, so these are some of the prerequisites. And I haven't put it here explicitly, but there's some things in linear algebra which also matter, like solving systems of equations, some iterative techniques for solving a system of equations. That also plays a role in some of these MDP topics. Not directly relevant for today's talk, but if you're in this area, you should be comfortable with linear algebra. And I've also listed some of the resources, some of the key resources, which I think I have definitely benefited a lot from when I was preparing for, when I was learning this area. So the first is this textbook by Sutton and Batu. So that's a simplest way to get into, many of these topics. And a slightly more rigorous flavor is given by the second textbook by Putterman. So you'll see, some of these claims that I'm going to make, due to want of time, I'm not going to be able to delve too much into it. But a detailed proof of many of these things you can find in this book by Putterman. And also there is this course by UC Berkeley, a course on AI, which I think is like really useful. Especially there are some of these hands-on exercises that you can try, some of the coding practices that you could go, and you can just try to they have a framework for reinforcement learning, okay, where you can visualize some of the algorithms that you'll see today. So you can just go and try to implement it. Of course, they have a different framework themselves. So there's a code base on which you go and enter your code. So you'll have to get familiar with the code base first. But I think if you are a student, it's certainly a useful thing to do. Okay, so these are some of the key resources. And also at the outset, I want to say that the topics that, I mean, the content of today's talk is something that I do in a course on AI at IIT Goa over about 10 to 12 lectures, okay, where each lecture is about 50 minutes, 50. Okay, so all that is getting compressed into 1.5 hours at max. So you can imagine that there's going to be some loss of information or many things. I'll not be able to go into too much detail, but the idea is to give you a flavor and make this area a little more accessible for many of you. Okay. Um, so with that, I want to just get started off with MDPs. So MDPs or Markov Decision Processes, these are there's a model actually which wherein you try to capture some temporal aspect of a process. Okay, for example, I mean, there's this racing car example that I've just shown on the right. So this is one of the sub problems that comes up in a self-driving car. Okay, so uh, you want to determine the speed at which the car should go. It's an automatic car, so the car has to determine what is the speed, whether it should go fast or slow. Just for simplicity, two modes, just fast mode or slow mode. And depending on whether you go fast or slow, the engine is going to be in a cool state, in warm, or it can just get overheated. Okay, so how do you model this, and how do you determine what is the speed to go at? Okay, so as I said, there's a temporal aspect. So maybe initially you start off with the engine being cool, and then you decide to slowly go, and then the engine maybe still remains at cool, and you slowly accelerate, and it goes fast, and so on. Okay, so this you can think of at there's a temporal thing coming in here. So this is at time equal to 1. There are these things that happen. So this is cool is actually the state of the system. Okay. And slow is the particular action that you decided to take. Okay. So this is what is happening at time equal to 1. And at time equal to 2, again, the car went back to a cool state, and then the decision was to go fast, and so on. Okay. So keeping this example in mind, MDPs, if you think of, they're characterized by states. So that's the state of the system at any time, couple of states, couple of actions, or it's also called control. Okay, and this is the decision that you make, okay, or you or the automator makes. And then there is a transition function, which is actually a probability. So you start off in some state, you take an action, and then you go to a next state. Okay. So the next state is not always like very, clearly determined. There's a probability with which you go to the next state. So the next state itself is a random quantity. And there's a probability of reaching that state S dash given the current state and the action. Okay. Was there a question? Um, Okay, fine. So there is this probability that comes up here. And in particular, there is what we call as the Markovian assumption. So if you've seen Markov chains, it's very similar to the assumption being made there that, if you try to look at the probability of, reaching some state at time t plus 1, given, the current state and the action that you took, right? These are the only two things that matter. Ideally, you have, probability of being at st plus 1 given st at, and you also have the history st minus 1 at minus 1, all of these things. Okay, and right away from time 1. Okay, all these typically should impact, where you be at st plus 1. But the simplifying assumption being made in MDPs is that it's just the previous state and the action that determines, or not determines, the previous state and the action that give you the probability of being at the next state. Okay, so that's what is the Markovian assumption. You can ignore everything else. So all of these you can ignore when you define the probability distribution. Okay, so yeah, of course, it's a simplifying assumption, but simplicity, biases something. Okay, so that is the next part, the transition function. And then we have the reward function. So each time you move, you were in state S, you took an action A and you went to S dash, there is some immediate reward that you get. Okay. So in the case of the racing car, if you're at cool and you go fast, and suppose you go into, the cool state itself. So I'm talking of this arrow here that I've drawn. So this happens, let's say, with probability 0.1. And since you're going back to the cool state and, you've gone fast, the reward, I've written this as 100. Okay. Whereas, if you go fast and reach the warm state, the reward is slightly less, 60, because you don't want to become warm too quickly. Okay. So like this, there are different, each of these transitions is associated with a reward. Okay. And finally, there's a terminal state, which is not always mandatory in every MDP. Sometimes, like in this case, there is an overheat state. So the overheat characterizes the end of the system. It's a bad state to be in. Okay. And so after the system reaches overheat, that's it, nothing else happens. In other examples, it could be a characterization of a good state also.
Can I
So
can I
and
just
sometimes you may not have a terminal state.
Divya, just one
Yeah, hello,
second.
Professor Sumit.
Yeah,
Yes,
yeah. The reward function you said R is S cross A to R, but then
yes.
you are showing three arguments in R. In
This
the
is the typo. Yes, this has to be S cross A cross S.
okay, 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 okay.
Thanks for pointing it out. Yeah. Yeah. So yeah, it's a yeah, it takes all these three arguments. And so what I've drawn here is one particular example, the race car example, and one possible MDP model for it. Okay. So yeah, these numbers are at the moment not critical, but even for any system, like designing the MDP itself can be non-trivial at times. Okay. And here, based on some things about the domain and some things that we as users prefer, I've put in these numbers. Okay. So for example, cool, when you're in a cool state, you go slow. There are two possibilities. Either you go back to cool with probability 0.8, and with a very small probability 0.2, you go to the warm state. and these two have rewards of 50 and 10 respectively. Okay, and from the warm state, if you take the fast action, either you remain at warm or you go to the overheat state. It's more likely that you go to the overheat state, and this is associated with a reward of -10, a negative reward. Okay, so like this, this is the way you model the system. Think of what all can happen at each of these. Choose a favorable probability distribution and a reward function. Okay, so this is what an MDP is. Are there any questions on an MDP, the components of an MDP? Yeah, so yeah, please feel free to stop me if something is unclear. Okay,
Excuse me,
so
ma'am.
yeah, so was there a question,
Yeah, ma'am,
Sanjana?
yes, ma'am. So, ma'am, these probabilities of for each action, how are they calculated? Like slow is pointed like that. How it is calculated?
So these numbers, this is actually a design choice. Okay, so when I model system, I have chosen these as the probabilities. So it's actually dependent on the domain knowledge.
Okay, ma'am.
Um,
Thank you.
Fine. So later we will move on to the setup where these probabilities and the reward functions, those you will not know it beforehand. You just have some system and you're observing some transitions like this. You're observing what is going on at each time period. And maybe you observe some things about the reward, but you don't know like perfectly. Like how I've given here, you may not be able to see, and that is what the reinforcement learning setup will get into.
Okay.
Yeah. Okay. So yeah, this is just the same thing that I explained. I've just written down the states, the set of actions, and all that explicitly. Now, one thing that I'm going to focus on is time homogeneity of these MDPs. So by that, what I mean that at time equal to 1 or at time equal to 2, whatever time step you are in, these probabilities, these numbers that I've written, that is not going to change. At every time in your entire sequence, you're going to follow the same process. Okay, so that is what is a time homogeneous MDP. Now, there are cases where you don't have time homogeneity, which is a lot more complicated. So these probability distributions, those will change depending on the time at which you are in. So for simplicity, let's just focus on time homogeneous MDPs. And then we have what is known as a policy. Okay, so policy is basically a mapping from the states to the actions. Okay, so for example, one policy could be that if your engine is in the cool state, you go slow. If it's in the warm state, you go slow. So this is basically go slow always. Yeah, and of course, in the overheat state, there is no action because it's the end of the process. So that's why cool and warm are the only two states which matter. And so like that, there are a couple of other uh, possibilities for policies. Go fast when you're cool, and when you're warm, you go fast. So this is always fast. And then you can have things like, when you're cool, you go fast, and when you're warm, you go slow, and so on. So you can have all these sort of combinations for each state. What kind of actions can you assign? Okay, so that is what is a policy. And again, we are going to look at time homogeneous policies or stationary policies, as they refer to it. Okay, so stationary policies, what it means is that, if at any point of time that you go to cool, so if I'm looking at the first policy, let me call this pi 1. So the first policy says that whatever time you are in, if you're at the cool state, you go slow. If you're at the warm state, you go slow. Okay, this is not going to change depending on the time. Okay, so that's what is meant by stationary policies. And again, we will focus on stationary policies for the purposes of this talk. Okay, so this is what is a policy, and a policy is what is of interest in the MDP literature. Okay, and so as I said before, there's this temporal aspect that comes in for MDPs. So like I said, at time equal to 1, maybe you're at cool, you went slow, then you get some reward. 50. So this is what was given by the MDP. And then you moved on to the cool state. And then at time 2, you were in the cool state, you decided to go fast, you got a reward of 60, and you moved on to the warm state, and so on. Okay, so this kind of a process can go on till infinity. Okay, so again, here there are two ways in which you look at it. So one is the length of the horizon. Okay, so how long does this process last? So one is it can go on up till infinity. Okay, so generally we'll say the horizon length is t, and one case is where t is infinity. Okay, so t is infinity, or it can be a finite horizon. So maybe something like after 100 time steps you stop. So that is a finite horizon case. But typically the infinite horizon is what is of interest in an MDP. Okay, so the overall reward that you get, so this is one such trajectory which I've listed down. So you can think of it as one realization of all these, probability distributions that there was an underlying probability distribution and a reward function. So one realization of it is this trajectory that you see here. And this is going to give me a total reward. If I sum this up, I can take 50 plus 60, 60, 50, 100, and so on. I can keep summing this up. And this is the cumulative reward. And usually, whatever action I take, I want to maximize this cumulative reward. But the issue here is, how do I now measure such an infinite summation? So if you take an infinite horizon case, you cannot, this may not give you anything finite. Okay. And also what is happening here is that the reward that you get at time 1 and time 2, they are weighed equally. Okay, so whether you get 50 first and 60 later, or whether you got 60 first and 50 later, that is considered as an equal. I mean, there's no distinction being made if you just take the sum of all these rewards. Okay, so ideally, immediate high rewards are better than a high reward at a later point of time. If you think of, compounding of interest and those kind of things. Okay, so these are two issues with this kind of, just taking a sum of all the rewards at, each time. If you do it that way, there are these two issues that arise. So in order to, ensure that first things remain finite and, you consider immediate rewards more important, there's this notion of discounting. Okay, so what it says is that you take some gamma between 0 and 1. Okay, and the long-term reward that you get, okay, summing up all these rewards across all time horizons, what you do is you also put a factor of gamma power t minus 1 for each time. So the initial reward at time 1, so this is r, so r1 is, this is at time equal to 1. Okay, so this is the most important. And then the second, at time 2, what you're going to get is R2. That is, scaled down by gamma times R2. Okay, and so on. Okay, as you move further and further, the importance kind of drops. Okay, though it doesn't become 0, but still it drops. Okay, and so this is what we'll use instead of going for the cumulative reward. What we do is we go for the long-term discounted reward. So it is also going to give the finite value, because this one you can see that if this is going to be less than R max, so where R max is the maximum reward that you can get from the MDP at any state action for, any value that you can get, any reward from the MDP, let's say R max is the maximum value. So this whole thing is going to be less than 1 plus gamma square plus so on. Okay, and this um, this is a finite sum. Can anyone tell me what this value is?
One upon one minus gamma.
Yeah, so this is exactly 1 by 1 minus gamma, and you have R max times this. Okay, so this is a finite value. So that's why this kind of way to measure and sample MDP trajectory is more useful than just taking a sum, at every time step. Okay, so this is what we'll go with. And yeah. And what we'll do is, because there is, so what I showed you here is it's one sample MDP trajectory. Now, the next time you sort of go over this process, you might get a different trajectory. So let's say at run one, and let's say we are just going to follow the policy pi of cool is fast. So when you're in the cool state, you go fast. When you're in the warm state, you go slow. We're just sticking to that. But then what happens is, because S dash given SA, there is a probability with which you go to the next state. And so because of that, you can get different kind of state transitions and rewards. And so one run maybe gave you this kind of a trajectory. And maybe the second run gave me a different trajectory starting from time equal to 3. Okay, so first 2 times you took cool, I mean, you were in cool, you took fast, and that was the same. But from the third step, maybe things changed. Okay, so each time you run, you might get a different trajectory altogether. And so what is of interest is the expected long-term discounted reward. Okay, so the long-term discounted reward, we just saw it. And here what I'm saying is we are interested in the expected value of this long-term reward. If you start from a status and follow the policy pi at every time step. Okay, so this is how you would evaluate a fixed policy. Okay, so this is under the policy pi. So assuming that at every state, you're going to follow this policy pi. Okay, and you can write a set of recursions in order to compute this. Okay, so the way to see this is, I mean, typically I don't like to, mug formulas. So one way to visualize what's going on here is with a tree. So let me just write it with a slightly different color. Okay. So let's say you started off at S, okay? And the action that you're going to take, we are going to evaluate a fixed policy. So we are going to take pi of S, this is the action. And then you can think of it as there's an intermediate state where the environment comes in and there's some randomness which plays. So there's this probability of going to S dash from S and pi of S. Okay. So this is a temporary state that we've drawn it as a rectangle or square. And then there are a couple of possibilities here. And maybe finally S dash comes along. Okay. And this is what manifests. So when this transition happens, there's a reward here which comes, which is RS, pi S, and S dash. Okay. And then once you reach S dash, you're again going to follow the same process. You're going to work with pi of S dash and so on. Okay. So you can think of a value that's associated with each of these states. So if in case you started from S dash, you would have got a value of V pi of S dash. Okay, if you were always following the policy pi. If you started from S, you would have got a value V pi of S. Okay, and this is an infinite sort of a tree, which is playing out in the back. Okay, and so in order to compute V pi of S, it is actually going to be an expected value because here there are a lot of possibilities. Okay, so there's an immediate reward you get, which is R of S pi S and S dash. And starting from next time onwards, you're going to get gamma times V pi of S dash. So it's going to be gamma times the reward you got in the next step from S dash and so on. Okay, and that whole thing, that's again an infinite or a long-term discounted reward from S dash. And that's why you can just write it down as V pi of S dash. Okay, so V pi of S is exactly the value, the same value that you would have got at this square node that gets propagated to V pi of S dash. And this is like a random agent which plays in. And this value is an expectation over whatever can happen, at just below. Okay, so that's the way in which you can write down V pi, how to compute V pi of S. Okay, and the next step I've just expanded it further. It's an expectation over S dash where the distribution is given by our transition function, probability of S dash given S pi is. And so you can just weight by that. So take a summation over all S dash, probability times this reward plus this part is essentially the same. Okay, so that's how you can compute it. Okay. Yes. Um, so what we were doing was this fixed policy and evaluating this policy. There are these recursions that you can write for evaluating a fixed policy. Okay. Yeah. So just give me a second. Yeah. So maybe we can just try to write down what this means, with one example. Maybe it's useful to do that. Okay. So I would like some volunteers maybe. So let's just try to take this policy, pi of cool is fast, pi of warm is slow. Okay. And what I'm interested now is in v pi of cool. Okay. So what matters is pi of cool is fast. So basically, let me just mark the transitions also which matter. So this one here and this one here. These are the transitions which will matter. Okay. So can someone just tell me how I would write this down? How I would plug in these expressions? Okay. No volunteers?
Point one.
Okay. So point one comes from this transition.
Yes.
So
100
P
plus,
point
in bracket,
one,
100 plus gamma times
yeah,
V by
gamma times v pi of
cool.
cool. Okay. So basically from that is the first transition. This one basically. Yeah. And
Plus
yes,
point 0.9,
it's 0.9
60 plus gamma of
60 plus gamma times,
V warm.
yeah, v pi of 1. Okay. So that's basically this transition. Okay. So the R plus gamma times v pi of this state warm. Okay. So that is how you would express v pi of cool. Of course, there is again a v pi cool and v pi warm, which is coming in. So that's why it's a recursion. So similarly, let's also just write v pi of warm. Okay, so here, let me put it with a different color. So v pi of warm. So in warm state, you're going to go slow. So it's basically this one, this transition, and this transition, which will count. Okay, so yeah. Can somebody volunteer to mention these?
Point 2,
Point 2,
10, in bracket 10 times plus
10,
gamma of V pi of warm
v pi of warm.
plus
That's basically
point
because we're
0.8,
coming back to warm. Yeah. Plus 0.8.
60 plus gamma of
Yeah.
V pi, cool.
Cool. Okay, so this one. Okay, so v pi of cool. Okay, so these are the two expressions or two equations that you get. And if you solve this, you're going to get the value of v pi of cool, v pi of warm. Okay, two equations, two unknowns. And so yeah, in general, as many as the number of states, you will have these components of v pi. And so you'll have that many equations. And yeah, you should use your linear algebra skills to solve these system of equations. Okay, so I've just written the expressions here, and you can substitute and compute and complete the computation. And also, as a homework, try to compute the value of all the four policies here. So I mentioned the four policies that are possible here. Try to write these equations and compute the values of all these four policies. Yeah, the same, you need to follow the same procedure. Okay. Okay, so now this is what we said about evaluating a given policy. Now, the question is, out of all these policies, is there a policy which is better than the rest for every state is? So what we mean by that is there is pi 1, you're going to get v pi 1 of s for all s. Okay. Now there'll be pi 2, and you can compute v pi 2 of s for every step. Okay, so this is going to be basically you'll have a vector. Okay, so something like if there were two states, maybe here, maybe you would got something like a 10, 9. Okay, so for two states, maybe something like this. Maybe the second policy gave a value of 11 and 18, something like that. Okay, so like this for each policy, you can get these numbers. And the question is there a policy which is better than the rest for every state? So if you look at these two policies, pi 1 and pi 2, for state 1, the first state, you had 10 and 11. So second policy was better. And yeah, even for the second state, the second policy was better. And so can is it possible to always say that there's one policy which is better than the others? I mean, it could have very well been that, here you had an 8. So in this case, you couldn't compare these two policies. Okay, but the result is that, actually you might have these kind of things. Every two policies are not comparable across all the states. But there does exist one policy, at least one policy, which is better than all the others. Okay. So yeah, so what we mean is that there is an optimal policy, and I'm not going to prove this. You can check these references for why that's the case. Okay. And so then the question is, how do you find the optimum policy? One way is evaluate every policy and compute VPI and find, which is the best. But that is a very naive approach, and you can try to yourself see how many policies will exist. Okay. So that's not a very good thing to do. So instead, there are these Bellman equations, which are built on the principle of dynamic programming. So what it says is that, the similar way in which we computed the value of a fixed policy, you can actually try to do something similar for the optimal policy as well, a similar set of recursions. So here the idea is that if we say V star, okay, is the value, if you start from S, and you're always going to take the optimal policy. So we said there is an optimal policy. So let's say you took that action, and there was an intermediate state where the environment plays out, and then you go to S dash. And here again, you are going to, once you reach S dash, you're going to take the optimal action for S dash. And like that, you're going to continue. Okay. So then the value that you get by doing this, that is called V star of S. And so here again, since it's an infinite sort of process, what happens here is you'll get V star of S dash. Okay. And so the way to compute V star of S is to take, I mean, there's one action that did this, but like if you take some other action, you would get a different path there. Okay, so this was A, and maybe here, if you had A1, you would get some set of other values. Okay, so out of all these actions, which one gave the maximum value of this quantity, the immediate reward plus gamma times B star at S dash? Okay, because at S dash also you're going to always take the optimal value. And whichever is max of all these actions, you measure that across all these actions, and that is the V star. So again, it's a set of recursions, but just the difference is there's a max here. It's a max over all actions. And this quantity, this expected value of R plus gamma V star of S dash, so that you can think of as the value associated with this state. So that is called Q star of SA. Okay. So yeah, so that will be useful later when we get into the RL framework and we talk of Q learning. Okay, so now these are set of recursions again that you can try to solve. But the issue here is you don't know where to start from, right? In the other case, you had a series of equations, some linear equations, which you could solve and get the solution. Here there's a max. So it's not exactly a set of linear equations. You need to basically do this computation, maybe start from some V star and try to work backwards and get it. But what is the base case for this recursion? There's nothing here. Okay. So value iteration is a scheme. It's an algorithm which tries to implement what these Bellman equations are. The recursions are called the Bellman equations, and value iteration tries to implement it. Okay, so the idea here is you start off with zero, assuming v0 is zero. So, so it's like saying you start at the bottom of this tree. Okay, so this is a huge tree, and maybe you cut it off at some point, and this is like a depth zero. Okay, and you keep building upwards and upwards to keep trying to compute vk at each level, and then you stop when it converges. Okay, so when, and the claim is that it will converge again. I'm omitting the proof of it. Yeah. Sarla?
Yeah.
Yeah, is there a question?
No, ma'am, no.
Okay, okay, fine. So you start off with zero and you keep building up on these values and till you converge. So that's the value iteration scheme. Okay, and you can actually do it for this racing car example, and I will just show you one demo quickly. But before that, I'll just tell you that this is one scheme for implementing the Bellman equation, the value iteration. Now there are other schemes also. So there's something called the policy iteration, which I don't want to spend too much time on. But the idea is, you start off with some initial policy, evaluate it in whatever way. So you can solve the system of equations, or there are iterative schemes for also solving a system of equations. In whatever way, your favorite way, you evaluate the V pi k, and then you try to get a better policy using this V pi's that you evaluated. So instead of V star, you use the V pi and you try to get a better policy. Keep trying to do this. And so this is like an iteration over the policy space. They keep moving to a better and better policy. And then there are also some techniques based on linear programs. Okay, so again, I mean, all of these recursions that we wrote down here, the Bellman equations, you can sort of write these down as inequalities. And the objective is always to maximize your V star. So you can write down some sort of a linear program to do this computation. So again, I won't get into these details. You can check it out. Okay. Fine. So let me just maybe just show you one snippet of code. Okay, so I'm just taking the same robotic car example. Okay, so what I've done is I've just, okay, so it's the screen visible, the Python code.
Yes, ma'am.
Okay, great. So here, the initial part, I've just set up the MDPs, the cool state, warm state, and all our transition probabilities, the rewards and everything. And I've just coded up the value iteration algorithm. So here, like what we discussed, the first thing is to evaluate, you set up the values as zero, and then you try to evaluate these, the expected value computations and get a max value. Okay, and keep on doing this. Okay, so your V keeps getting updated, your value function, it keeps on getting updated. And you keep on doing this over a couple of iterations until convergence. So your convergence is when your value function, your vector of value functions doesn't change anymore. Okay, so I'll just run this once. Okay, so here what has happened is I've just printed out for each iteration what the values were computed as. Okay, so initially, the values, so this is V stars, it's trying to compute V stars. So V zeros were all zero, and after the first iteration, these were the values obtained. And it kept getting changed after each iteration. And I've also printed the policy that it came to. So which was the action which gave, the 64, right? So that was fast. Okay, and which was the action which gave 75, that was slow for the warm state. Okay, and so what happened is this ran for a couple of iterations, and the final value, after about iteration 6 or so, it has converged. and the value is 118, and for the warm state it's 108. Okay, and the optimal policy is this: at the cool state you go fast, in the warm state you go slow. Sort of makes sense with respect to what our MDP model was. Okay, now at the outset, I just want to say that here, even in the after the first iteration, it converged to the optimal policy, but it took some more iterations to converge to the exact value. So the values here were not the correct values, and that's why it took some more iterations. Okay, and this is just a feature of those numbers that we have given. Maybe the numbers are like very, in the first step itself, it's able to distinguish. But you can try playing with different numbers, different reward functions, and see what happens. Okay, yeah. So let me just go back to the slides. Okay. And yeah, so yeah, I would urge you all to try and implement the value iteration algorithm. Okay. And also the policy iteration. I mean, you can go over it and try and implement. Okay. So now moving on to the RL framework, we've just looked at MDPs. I mean, we've looked at how to find the optimal policy. Now in the RL framework, what happens is these two, the transition function and rewards, are unknown. Okay, so there's an agent which is in some state. The agent takes an action. The environment then does something, introduces some randomness. Okay, and then the agent moves to the next state, and the environment also gives the reward. Okay, but the underlying probability, so here there is a stochastic process which is playing out. So basically the same transition functions are playing out, but you don't know that. Okay. And so now if you had to choose the optimal policy, how would you go about? Okay. So here broadly, there are these three frameworks. So one is a model-based learning, which is like what happens in classical ML framework. So you obtain estimates, there's some data, you obtain some estimates for your transition probabilities and rewards. And then you think that, I mean, you assume that this is your model, your estimates give the correct model, and then you just go ahead and compute. I mean, you use the Bellman equations, assume these are the correct parameters, and do the computations. Okay, so that is one framework. The other two are typically what are more commonly used, are they're more popular. Okay, so I'll just quickly talk to you about the model-based learning and then tell you about the other two methods as well. So in the model-based learning, what happens is there are a couple of, episodes. For example, in this case, this is not the race car example, but this is a grid world, what is called as the grid world example. So where there is a board and some positions, and it's about how you move across this board. But the only catch is that, maybe here there are just A, B, C, D, E. There are just 5 positions. A and D are the terminal positions. So once you reach A and D, you are done. Okay, you have to exit, the game ends. But the catch is that at B, if you take a right action, you're not guaranteed that you will go to C. Okay, so I mean, if this grid above was an active position, then you could also end up going there. And maybe at C, if you take a right, you're not guaranteed to reach D. You might even reach A. Okay, so it's sort of like a keyboard, a layout of a keyboard, but a very noisy keyboard, a very badly performing keyboard. You can think of it that way. Okay, so now um, I'm just trying to demonstrate what model-based learning would do here. So there are these episodes that you observe. So episode is just nothing but one run of moving on this grid. Okay. So let's say you were always going to follow this policy. At B, you would try to move right. When you came to C, you would try to move right. At E, you would try to move up. Okay. So how would you evaluate the value of this policy? You don't know the probability with which you will go to an off position, right? So the way anybody would do is you'll just try this out few times. You will try the keyboard out, and then you get a hang of it. So that's what model-based learning is doing. So first time when you went east from B, you went to C, and then you went east, reached D, and at D you exited, and these were the rewards that you got. Okay, and so on. A couple of times you did. maybe the fourth time here, you see that, you started off from E, okay, and then you went north, okay, and you reached C. At C, you took an east, but you went to A, okay, instead of going to D. And these were the rewards. Okay, so a couple of things you tried. And now, based on these four runs, these episodes or these runs, what you can do is you can see what's the probability. So if you want to measure the probability of reaching C, given you started from B and took an east, this is just basically the number of times. I mean, you can just do this by the number of times you this kind of a transition happened, okay, divided by all possible values. So I'm just going to write this as some S. So all possible values that you could have reached by going from B and taking an east, okay. So that's these numbers, okay. So similarly, you can see C, east, and D. So that's basically this one, C, east, and D, these three, but here C, east, you went to A. So that's why the probability becomes 0.75. Okay. So like that, it's just a frequentist estimate that you can get. And similarly for the rewards, you could do the same thing. Okay, so that's model-based learning. And once you have these probabilities and rewards, you just try to use value iteration or policy iteration or whatever your favorite method in the MDP literature to get the optimal policy. Okay, so that's model-based learning. Now, the issue here is that there's a two-stage sort of a process. You learn the parameters first, and once you have enough data, which you don't know how much is enough in the first place, and once there is some estimate, only then you apply the recursions. Okay, so this is not a very smart thing to do. It's okay sometimes, but yeah, it's not a very advisable thing to do. So can you do something smarter? Okay. So that's where these other techniques like temporal difference learning and Q learning come into picture. So here, let's just again look at learning the value for a fixed policy. There is a policy, you just want to be able to say what the V's are. So if you remember, this is V pi computation was an expectation computation. Okay, and the issue is you don't know the probabilities, these probabilities which are needed for this expectation computation, that's not known. The rewards, this is also not known. Okay, so one way to do this is somehow construct samples. So this is actually a random quantity because S dash is random. So this entire function, it's a function of S dash, so it's random. So construct samples of this quantity and then use the law of large numbers, okay, and get the mean of these numbers. Okay, get the mean of these samples and use that as V pi. Okay, that's what you would probably do. And that's what exactly is temporal difference learning. So the idea, just let me just illustrate it. So one thing here that we also try to do is um, it's important to get a moving average. For example, in model-based learning, what happened is you had 4 episodes or maybe some 100 episodes, whatever it is. At the end of it, you get a model. Okay, but the question is, can you also have a running estimate? So after you see each transition, can you get an estimate of V pi? And can you keep making the estimate better and better? Okay, so what helps is this idea of moving averages. So let's just take this example where there's a random variable h, maybe the height of the attendees. Okay, and we want to estimate what is the average height or the expected height. And so maybe I ask each one of you, what's your height? Okay, so then I get these numbers. So these are samples of the height of the population. Okay, and then what I do is um, I can, I mean, so the formula, what I would use for E of H, that would just be the sample mean, right? So I will just take summation HI, or let me just write this properly, H1 plus H2 plus so on, plus HN. If I had N samples, this is how I would compute the average, and I would use that as a proxy for the expectation. Okay, so that's what I would do with N samples. Let me call this as HN hat. Now, if I had N plus 1 samples, again, what I would actually want to do is this. okay, plus hn plus 1 divided by n plus 1. Okay. But now what I've done is I already, after I got the nth sample, I had this estimate. I can sort of reuse that to compute hn hat, I mean, h hat n plus 1. Okay. Because this summation that I want, this is just nothing but, hn plus 1 by n plus 1 plus h1 plus so on plus hn by n plus 1. I've just split this fraction into two parts. Okay. And what I can do is, instead of the second term here, I can just write it in this manner. Okay. Hn hat times n by n plus 1. Because hn hat is just h1 plus so on plus hn by n. Okay. So n times hn hat by n plus 1 is going to give me this second term. Okay. And I can even go one step further. So here there is, I can think of this as some alpha and this quantity as 1 minus alpha. Okay. So where here alpha is in particular 1 by n plus 1 and this is 1 minus alpha, right? And actually it turns out that this alpha, I don't even have to set it as 1 by n plus 1, when I implement this. I can fix it to be a very small quantity and go ahead. I'm still going to get the, a reasonable estimate. Okay. So I'll just again show you this illustration. Um, yeah. So here what I've done is I'm just taking a normal distribution. Okay. And I'm taking a normal distribution with mean 5. Okay. And I'm taking samples from it. And I'm just going to estimate the value of the mean. Okay. So I should get back a value of 5. Okay. And what I'm doing is I'm taking this alpha as 0.01. Okay. And so let's see what happens. So maybe let's just take maybe 3 samples. I'm starting off with an estimate of 30. So my assumption is, okay, let me guess a very wrong value of 30. And then I'll see how my samples help or don't help. Okay. Okay. So you see that after 3 samples, it's not changed too drastically. Okay. So from 30, it just kind of dropped. But if I take enough number of samples, let's say maybe I take about 500. Okay. So you see how these values have started changing at some point, right? So yeah, so initially the estimates were quite bad, 27, and it moved slowly. And but after some point, after I had enough samples, I got enough numbers, it's come very close to 5. Okay. So this alpha, of course, if you keep 1 by n plus 1, it is accurate, but it turns out that it's not very crucial. Okay. So this is the theory of stochastic approximations, which enables you to do this. Okay. Um, so yeah, so that's the idea in temporal difference learning also. Since you want to estimate V pi of S, which is an expectation, you construct samples of this. And in order to maintain a moving average, you use this kind of a computation. And so eventually, once you have enough samples, you will reach the correct value. Okay. So the whole algorithm goes like this. You initialize your V hat. I mean, V hat is what I'm using because it's an estimate. Initialize this to something, maybe 0 or any value. And then you observe this kind of a transition in your episodes. S pious, because that's the action. I mean, that's the policy you want to evaluate. So this is one action. Goes to S dash and you get a reward. And the sample is a sample of this random quantity. So you take it as R plus gamma times V hat, because V hat is all that you have. Of course, it should have been the original V pi, but that's what you want to compute. You don't have it. So you just use V hat as your estimate. And then you update your estimate using this kind of a quantity, 1 minus alpha times the old value plus alpha times the newly generated sample. And then you go to S dash, you keep doing this. Okay. And once you have enough samples, yeah, the hope is that V hat comes close to V pi. And this sample, this sort of a thing works because once you have enough, the importance of each of these kind of reduces. That's also a reason why you use alphas as a very small value, so that one sample doesn't sort of bias the whole thing. And so the importance of v hat also that you're using here kind of, okay. Yeah. Okay. So maybe we can just see this on one example here. So let's say, so this is the algorithm that I mentioned. And again, the same model-based learning example that I showed you for this grid world. Let's say we had the states here are A, B, C, D, E. So let's say initially we had, all of these as 0. So for B, C, D, E, all of these are, let's say all of these values are 0. Okay. So now let's say I saw this transition B east C minus 1. Okay. And I want to, make this update. So can any of you volunteer to tell me what this is going to be? So we had pi of, I saw this S is, so this is basically my S. This is my pi of S. And then I have S dash and R. Okay. So what would it look like? Okay, anyone can volunteer.
V pi of b
B,
is equal to 1 minus alpha
1 minus alpha,
v hat of pi again b
again B, yes.
plus alpha times minus 1
Yes,
plus gamma times
yes,
v
gamma
hat pi of c.
of C. Okay. So let's say our alpha is, let's take alpha as 0.1. Okay. So this is going to be 0.9 times V hat pi of B, which was initialized to 0. Okay. Plus 0.1 times minus 1 plus gamma. Let's take gamma as 1 because, here it's not going to be infinite horizon ultimately because there are two terminal states. Okay, so this is going to be 0 again. So this value is going to be minus 0.1. Okay, so yeah, so V hat of B changed from 0 to minus 0.1. And next time when you see a B being encountered, again, if you had to use V hat pi of B, you use this. And so you can keep on doing this. For each transition, you can keep making this update. Okay. So that's how temporal difference learning works. And at the end of it, hopefully you've converged to the correct V hat. Okay. So now this was about evaluating a fixed policy. Okay. A fixed policy by finding the value V hat without knowing anything about the transitions or the rewards beforehand. Just by seeing some data, how do you do this? That's what we did. Now, the same thing we want to do for ultimately the optimal policy. That's our interest in MDPs and RL. So remember the Bellman equations that we saw. If you knew everything, this is how you would compute V star and Q star. Okay. Q star was an expectation computation, but V star had a max over actions. Okay. And the idea in temporal difference learning was to use this notion of, if you have an expectation somewhere, use the law of large numbers, get samples, and compute. Okay. So here, the issue is that V star has a max over expectations, not directly an expectation. So the same thing in temporal difference learning will not work with V star. Okay. But what helps is, you can do the similar thing with Q star because Q star is an expectation computation. So you can just take samples here at this stage and then, try to compute V star using the Q stars. Okay, so that's the idea in Q learning because you're trying to maintain estimates for these Q stars. Okay, so the same idea. Okay, so you maintain some estimates q hat, but now it's a function of both your state and your action. Okay, and then you need a sample of this quantity. Okay, so whenever you observe some transition, let's say that there's some data, some episodes you're getting from S A S dash R. Okay, so these are standard transitions. Then what you do is you have your old estimate, which is q hat, and your new sample is R plus gamma times, it should have been V star, but you don't have V star as such. So you just express it as max of q hat. So because that was exactly what this was, V star of S is, if you see this expression, this is just max over A, q star of SA. Okay. So exactly same thing you do here. You wanted V star of S dash. So instead of that, you just write gamma times max over all the next actions, A dash. Okay. And Q hat of S dash A dash. Okay. So that's your sample. And you keep doing this. You keep maintaining your Q hats. And finally, once of course, at each point, you can also find your V hat star of S. So this is just going to be max over all the act. The whole idea in Q learning is, as I said, to maintain these estimates for Q star. Again, using the idea of law of large numbers and constructing samples, and then use that to in turn construct your estimates for V star. Okay, and yeah, so this is the thing. Now, one thing here is a difference from temporal difference learning is the assumption was that in TDL you assumed that all your data was coming from a fixed policy. Okay, the actions in particular were coming from a fixed policy. Now, the thing with Q learning is there is some flexibility because you're trying to you're trying to ultimately find the best action. So you have control on choosing what actions you want to take here. Of course, finally, what S dash and R comes, that the environment decides. But there is some design choice here in what actions you want to take. Okay, you don't want to always take just one action. You want to have some diversity because ultimately you're learning something q hat of SA for all SA. You want to have good estimates for all the actions. Okay, so you should ideally try to cover the entire spectrum of actions for every state. Okay, but at the same time your goal is you want good rewards. Okay, so there's some kind of a trade-off here, which is called the exploration exploitation trade-off. Okay, because exploration is you want to explore many actions, and exploitation is you want to get good rewards. Okay, so now how do you achieve this kind of a balance in this trade-off? So the ways to do that are the couple of ways. Okay, so one is just pick a random action which will do complete exploration but no exploitation. So by random action, what I mean is whenever you come to some state S, you pick one of the actions and with some probability 1 by A, uniform, or you can keep some probability distribution here and just do an exploration. Now, this is not going to do any exploitation. So what another suggestion is to do this epsilon greedy approach. So what it does is, yes, you do this random action with some probability, which is epsilon. Okay. Now with probability 1 minus epsilon, you can compute the best action. So you are maintaining these q hats. Okay. And you can find max of q hat SA. Okay. For every A. Max over all the actions. And so this is the best action. So the action which maximizes this, that's the best action. You can choose that. Okay. So that you do with a probability 1 minus epsilon. Okay. But you don't always choose this one because maybe, you got lucky few times in getting, good. This action was the good action. But actually, maybe it's not always the best thing. So that's why you keep some proportion of time for exploration, taking the random action, and sometimes you take this best action greedily. Okay, so that's the epsilon greedy principle. And then there are also some more techniques. These are slightly more sophisticated. So one thing is, um, if you take the max value of q hat SA, so that is an exploitation strategy. You're taking the best always. Now, instead of doing that, you keep some kind of a number and a value here, some sort of a confidence bound. And this second value here, it's inversely proportional to the number of times action A was picked. A was picked. Okay. So if you picked the action A very few times, then this number becomes very large. Okay. And so then you are forced to go for this action. So at least few times you'll have to pick every action. And once you have picked this action enough number of times, this estimate sort of takes prevalence. Okay. And of course, the exact value of this confidence bound, it depends. Okay. So depending on, so there are some results like depending on what underlying probability distribution, the nature of the underlying probability distribution, you might choose different confidence bounds. And this is chosen, there's some principled way of choosing this confidence bound. Okay, it's not a very arbitrary choice. There's a very principled way of fixing it. Okay, so this is called a UCB kind of a scheme. Okay, so these are some of the strategies, and maybe I'll just show you a demo of just the epsilon greedy approach. So I will just do it with the same racing car example. Just go back. So Krishnaveni, how am I doing on time?
You have 15 more minutes left.
Perfect. Okay. Okay, so what I'll do is I'll just take, I've just implemented a Q-learning scheme. So this is exactly the same MDP that I showed you value iteration for. Okay, so the first part is just declaring all of these, the parameters of the model. And there are a couple of things I was trying here. So let me just get to the Q-learning setup. So in Q-learning, what I'm going to do is I'm going to input the number of episodes. Okay. And so, these numbers here that I've input, the transition probability rewards, it's not really needed for a Q-learning setup, but since we are simulating the process, that's why it's needed. Okay. I'm not going to use it in my computation of estimates. Okay. So what will happen here is I'm just going to simulate one episode. Okay. And so here you can see I have this epsilon greedy probability. So there's a probability of epsilon for choosing the random action. So here there are two actions. There was a slow and fast action. Okay. And then I have a best action. So my initial Q values, I've initialized it as 0 for all my states and action pairs. Okay. And then what I'm doing is I'm going to take the best action. I'm going to see what's the best action based on my Q value estimates. And so that's the epsilon, that takes a probability 1 minus epsilon. Okay. And so then that's the action is, picked. That's again, it's a probabilistic thing, right? So it's it's some probability I'm going to pick each of these actions so that I'm going to simulate. And then once I've picked this action, the next state is a draw from the environment. So that is where I will use this transition probability. Okay. And so that is a draw. So that's a simulation from the environment. And also the reward that I get, that is also something which is coming from the environment. Okay. And so that's going to give me the next state and reward. Okay, so the episode is now going to have these things, the state, action, so the sample of 0 is the next state, basically, and then the reward. And now my Q values, I'm going to update it with the expression I showed you, 1 minus alpha. So the alpha that I use, that's also called the learning rate. Okay, so 1 minus alpha times the Q current estimate plus alpha times this quantity, which was, R plus gamma times the max Q values. Okay, so it's going to update the Q values, move the state to the next. Okay, and then keep doing this. okay, until I reach an overheat state, or I also have a bound on how big I want my episode. Okay, so if I cross that number of transitions, also I will just leave. Okay. Okay, so that is how this Q estimates are going to work. So that's the Q learning framework. So let me just show you a run of it. So I'm just going to take epsilon as 0.2. So 0.2 is the probability of the random action. Okay. And let me just start off with my number of episodes as I'll just take one episode and maybe just two transitions. Okay. And yeah. So here what it's saying is I've done Q learning. Okay. And at the end of Q learning, these are my estimates. Okay. So cool and slow, that is 0, cool fast is 0.6, warm slow 0.603, and warm fast is 0. Okay. So not such great estimates. So if you remember, like I showed you value iteration. And so if I look at the actual best values for the optimal policy, I've also computed that. Okay, so the best policy here actually turns out to be in the cool state you go fast, and in the warm state you go slow. That's what was computed earlier. I showed you. So the values should have been this 108 and 100 and 118 and 108. Okay, so if you look at cool, slow, cool, fast, so the maximum here is 0.6, which is like very far away from 118. So this is not very good. So the issue is I need more data. Okay. So just give me a second. Okay, so now let me just increase my number of episodes. So I just fixed one episode and with a length 2. So if you look at my episodes, it's just 2 transitions. Come on, with 2 transitions, I just cannot really learn much. So let me just keep 10 transitions. Let's see how these estimates change. So there's some more change, right? 0.59, 0.6, maybe some of the other values also got updated. And maybe now let me make it some 50 episodes, and which each episode length is about 10, not more than 10. Okay. So my estimates are getting better and better. So 60, 21, 42, and minus 0.4. Of course, with this, I have the optimal policy. This is going to give me the right policy, but the numbers are off. Okay. So I can maybe let me just take larger episode lengths and maybe something like 100. Yeah. So here, if you see, now cool, in the cool state, there is slow is 86 and fast is 112. Okay. So the fast action was the better one. Okay. And if you look at the actual values, the fast, here it was 108 and we got up to 112. And for the warm state, the best one was to go slow, right? And this was 104. The true best was 108. So it's sort of converging closer and closer to the correct values. So it turns out to be working. Okay. And you can actually play around with all these different values of epsilon and the learning rate, and to, just see how things converge. There'll be some difference in the convergence properties, but ultimately it will converge to the correct values. Okay. So Q learning does work. Okay. Um, yeah. So are there any questions on this? If there are none, maybe I can just show you one more demo of Q learning. Maybe I can, yeah. So there's some more aspects of Q learning like which can be improved. So maybe let me just come back to that. So one thing here is, when I told you about the Q learning algorithm, you need to iterate. You need to maintain these estimates for every state, every action. Okay. Now, I'm not going to go into too many details of this, but if you have a very large state space, okay, which is what typically happens in applications like chess or any gaming sort of a thing, when you have large state spaces, you need a lot of data to get some reasonable Q estimates. Okay, so this kind of an approach where you wait for enough data for every state action, that doesn't really work. It's yeah, I can also show you some demos where you can see that it doesn't work. Even for a slight increase in the number of states, you need a lot more data. Okay, so the approach to handle this is to sort of generalize QSA, this Q function, using some other form. Okay, so one way is to approximate QSA using some linear function, using some notion of features, something which depends on the states and actions, and use some kind of weights. And now instead of exactly maintaining Q estimates, you maintain estimates for W. Okay, so sort of like how you do in regression, I would say. Of course, you need you need these some numbers here in order to be able to learn your W's. But yeah, so this is one technique that people employ. So kind of use the same Q learning algorithm, but modify it in order to have this kind of an objective. I mean, not modify it to have this kind of a model for your Q function. And now there are also all these deep learning based techniques, which is called deep reinforcement learning. So instead of this linear approximation, use deep learning models. And I've also seen methods where people have tried to use things like decision trees and, a lot of, whatever ML techniques which are there, try to plug it in order to, make estimates for your Q function. Okay, so that is one. There's a lot of research which is currently going on in this space, the deep reinforcement learning space. And there are also some other topics which I've not really delved upon here. So one is policy gradient. So in policy gradient, what happens is that's also a way for getting an optimal policy in just traditional MDPs. So we talked of value iteration, which I told you something about policy iteration and LPs. But policy gradient is another scheme where you sort of devise an optimization algorithm. So basically, there's some kind of a loss function which is defined as a function of your policies. And you're trying to ultimately solve this, find the policy which minimizes your loss. And try to, develop some sort of gradient descent kind of schemes for this loss function. And yeah, kind of an iterative scheme again here. Okay, so that is policy gradient. And another thing we didn't speak of, I just talked to you about policies. By default, I talked to you about deterministic policies because deterministic policies are optimal for the kind of MDPs I told you about, like time homogeneous and stationary policies and all that. So there's no need for randomization there. But sometimes when you go into what are called these robust models, so in robust models, that's another way of approaching, you know, reinforcement learning in quotes, in the sense that when you don't know the probability distributions or the reward functions, one other paradigm is to assume that you have a class theta of probability distributions. Okay, and then sort of go for worst case. So ideally you want to, you know, yeah, you want to minimize some loss function defined over your policies. But maybe, so this is the case if you have a fixed distribution. So L, maybe it's an expected loss. Okay, so expected value of loss in terms of the policy pi. Okay, but now maybe you don't know the underlying transition probabilities, but you only have this class theta of probability distributions and go for some sort of a worst case. So this P belongs to this class theta, something of this kind. Okay, so that's the idea in these robust models. So these randomized policies sometimes play a role here when you go into the robust framework. Okay, but these are all things which currently is a lot of research going on here. Okay, but yeah, it's these are sort of advanced topics. But one thing I can just demonstrate is this issue with large state spaces and this need for, these approximations that's really there. Okay. So Krishnavini, how much time do I have?
I think, yeah, ma'am, I think we can wind up and open a Q&A as well.
Okay, fine. So yeah, so I think I mean, one thing, like, just before I wind up, just I want to just mention that, there is this website, right? I mean, the CS188 webpage that I told you about, the CS188 code base. So there is this entire set of practice exercises on reinforcement learning. And you can see how RL is going to get applied into games like Pac-Man. Okay, of course, there's a grid world thing, but there's also Pac-Man. Okay, so they don't have a illustrative figure, but you can see how it gets used, and you can actually build your own agent which simulates Pac-Man, which plays Pac-Man, and it does very well. And there you can see all these issues of large state spaces, why things don't work, and all that. So I'd urge you all to get into it. Okay. So yeah. So I'm open for any questions. Yeah.
Yeah, so yeah, thank you so much, ma'am, for the tutorial. It was very informative. I think it helped everyone get a good understanding of MDPs, value iteration, policy, model-based learning, and reinforcement learning. As you said, this is a quick 90-minute compressed version of the AI course taught at IIT Goa, and it's an honor to be able to bring this to everyone through ACM. So yeah, I think now we can open the session for a Q&A. If you have any questions, feel free to unmute and ask or put it in the chat box. I guess there are no questions.
Just
Okay.
maybe one. There is this multi-arm bandit problem, and it seems it's a kind of temporal version of multi-arm bandit. Is that right?
Yeah. So you're right. I mean, multi-arm bandits is like very closely related to, RL. So even there is this exploration, exploitation trade-off which comes in. One difference in multi-arm bandits is you don't have this notion of states as such. It's sort of like
Hmm.
a single state um,
Yeah.
MDP, to call it. And the issue is just with actions, and different actions giving you different rewards, and the rewards are like random. Um, so that's the thing. So of course, all these UCB bounds that's come from the multi-arm bandit literature, actually.
Okay.
Yeah.
I think there's a question in the chat. Anish has asked, in case of deep reinforcement learning, how does the reward system help find gradient for backpropagation?
Okay, so how does the reward system help find gradient? Um, so the reward system, okay, I'm not sure if I get your question fully. The reward system, it's actually a consequence. I mean, there is some randomness which is there, and the rewards can be random. And that's just something which is coming in through the transitions. Okay. So in terms of gradient or back propagation, you need something more. So here, let me just go to that slide. So so even if let's not get into the back propagation step, even for the linear function approximation case, there is this WIFI. Okay. And there's some notion of gradients that you have to define, even, to get into this, to be able to find this W. So something of this form you need to do, right? WI is WI minus some sort of a gradient. There's some appropriate loss function that you have to define here in terms of W's. Okay. So similar thing you need to do even for the deep learning context where you would have used back propagation. So the whole thing there is just about, efficient computation of these gradients, right? That's what back propagation does. Okay. But so all those things remain the same. It's not directly dependent on the reward system or the reward structure as such. It's based on your transitions. Again, you will construct some samples of, whatever there was. This Q function was an expected value. It's an expected value which is getting approximated using linear functions or your, functions that you would use in your neural network. Okay. So as such, the reward system itself doesn't play a role there. It's only about, how you define your loss function, and, that's going to affect your gradient. Okay? So Anish, I don't know if I answered your question, or was there something else?
Okay, I think there are no more questions. Let's find out then. Yeah. Thank you,
Great.
ma'am. Yeah. Thank you everyone
Thanks
for
a lot
joining
for
in. Yeah.